Okay, so welcome back. So let's start our next lecture by Yuri Prokhorov.
Thank you very much. Maybe I recall what I did yesterday. Suppose I will change notation a little bit. The basics as you know. Suppose it's surface conic one. So if k square is equal to 0, then x is birational x over birational rigid, super rigid. So there is only one polygonal structure. Okay, x square equals 1 or 2. Let's read the 2. Then x over z is birationally rigid. This means that the conic bundle structure is unique modular birational automorphisms. And x square equals less or equal to 4. Then x is not rational. And x square greater than or equal to 5, and x is rational.
If there's a point.
Yes, yes. Thank you. Moreover, we are interested in this part. Since this is birational trivial. Moreover, in under this assumption, any modifiable space I related to circuit spring I needed for three-dimensional. So I just repeat what we have. So suppose k x square less or equal to 4, and x over this is modifiable space, two-dimensional. So it's either Delpezza or conic one. So we have only few possibilities for link. That is link. There are only few possibilities. First, it is like this. We have Delpezza of degree 4, with Picard number 1, blow up of a point, and we have conic bundle of degree T over the base. So maybe like this. On this level, we have Picard number 1, this level Picard number 2. Type 3, it's inverse. To this, just like that, we have here Delpezza. Here we have conic bundle. And in the same time, we have a low-down structure. Here. Another one, type 2, and elementary transformation. Conic models. And type 2 transformations like this. Here we have variety Y, which is a delta degree 1 or 2 with Picard number 2, and we have to move down. Is working. So here delta of degree 3, 4, 3 or 4 or 2 is, and we move close point and go down. We can regard this as position with Bertini Geyser evolution. In the pencil, we have evolution, and we change this structure. And finally, by 4, also related to the person degree 1 or 2, we have X, and we have 2 conic bundle structures. Here degree 1, 2, 4. This guy is Delpesa is Picard number 2. And it has 2 conic bundle structures. Again, they interchange by in the case equals 1 or 2, we have Bertini negated evolution and interchange structure. In degree 4, this is a little more complicated. Typically, we have no such evolution, but we will have such a diagram. So that's so. This classification can be easily deduced from my first theorem I proved yesterday, because you see everywhere upstairs we should have delta. So anti-canonical class, that variety is ample. So, for example, in this case, we computed conic bundles when conic bundle has anti-canonical anti-canonical class. So this immediately follows from the first theorem. Okay. So and as a consequence of Sarkis theory, we know that how decompose Birational maps between varieties of this type. Okay, now I'm going to speak about high-dimensional generalization. Unfortunately, this this number is behaves not so good in high-dimensional geometry. So for conic bundles, we it's better to speak about discriminant. Here, discriminant is equal to 8 and 6 Or moreover, yes, they are told that the best variant is that the dimension of this linear system. In this case, we have four in this case we have non-negativeness of this linear system, and in this case we have so these things are quite generalizable in higher dimensions. Because now you see, now I am going to speak about gain standard conic model. And I assume that the field is algebraically closed. And for safety, then it's characteristically why? Because I want to use MMP in generality. Okay, so you can expect that the things are more or less generalizable, but there is an example. Two examples that show that they are not quite like this. First example is First example is take a cubic leaflet in P4, move one, and take a line. So this is standard thing that we can blow up line, and this we get here finally Picard number 2, and it has another contraction in P2, and this map is just projection from a line, and this is a conic bond. The fibers are residual conic to this line, and if you want to compute discriminant, degree of discriminant, we take the here another line, and they back will be here cubic surface with a conic bundle structure, and we know that it has 5 degenerate fibers. So intersection degeneracy locus of this one with restriction conic bundle gives us degree 5 subscheme. So just conclusion is the degree discriminant. This is an easy classical example. We know that from Clement cricket that cubic is non-rational, so this is non-rational. Another example. We'll start by panel. It's like this, quite similar. We start with P3 and take here curve degree 5, degree 7, and genus 5. This curve is just obtained by projection of canonical curve from a equation. So we take canonical P3, P4, fix a point, and project. You get things like this. Again, we blow usual blow with that variety X, and here again have conic vinyl structure. This again fun. This map is given by a linear system of cubic passing through cubics passing through this map. Again, since projection, since pullback of a line here is a cubic surface, what we have is that the degree of discriminant is important. But this what about expression? And what we see that the linear system 2, 3, delta is empty. According to our expectation, you should have a rational one, but we could have two possibilities. It turns out that this is only exception. No, only known exception. So,
Dimension 3.
yes, everything is dimension 3. So the expectation is that conic bundle has that it acts as rational. It cannot leave either empty or axis belongs to some bounded number. Of possibilities. Of course, we should consider this conic bundles modular fiber-wise equivalence. For example, if you draw a point on this base, we can extend just make the base change and get conic bundle over F1 and so on. So we can and I told yesterday that at least these numbers are pairwise rational variants.
Just make sure we understand. So the problem is not with the second example, but with the first example.
Yes.
The second, but it matches.
Yes. I mean that only two.
Yeah, but
To be more precise, this conic balance are different. Again, yesterday I told that there is more more delicate invariant, which is double cover. This is hybrid scheme which classifies components of degenerate fibers. And the type of this double cover is different. Yes, examples. In fact, since it's a plane curve, we have standard thick characteristic. This is half. This is just coupling section. And the double cover is given by some order 2 element in Picard. So once we have H1, theta characteristic, we have another one. And it depends on the parity of this one. In this case, theta characteristic is odd. In this case, it's even. So
what is not even?
but
What is odd or even? I couldn't understand.
what is
What is odd or even?
this is parity of this theta characteristic. Parity means that parity of space of sections. Okay. So expectation is like this. This is conjecture. So this rationality question holds throughout rationality conjecture and holds modular some bounded number of families, Birational families. But in fact, we know that this is just one element. Stronger conjecture is that it's a modular that just this exception. Okay. So but in this case, both of them found already, but you see again, once again, this all the problems we consider modular blow of the base. We make roughly speaking base change and get more and more examples. Now maybe yes, but anyway, in this cases, this of both varieties are final. In fact, this is embedded in this cross the2, and it is a complete intersection there. Okay, now it seems there are a lot of choices for the base. Maybe we want to minimize the base. Now somehow run the minimal molecule. In fact, it turns out this is possible. The theorem. This reformulation of maybe we know on tracks, but maybe now it's this point of view is more more important. We can run one a plus 1/2 delta NIP on the base in the following sense. If this divisor is not F, then we can we have there is of course nothing. This is just we have sequence of contractions. And in fact, here we have standard conic bundle. But the statement is that we can run it in the category of standard conic bundle. So on each step, we have commutative square. So that upstairs we have just birational map, not necessarily morphine, and each fi xi is standard component. In particular, all the surfaces that move. And this horizontal errors are extremal contractions. Negative is negative with respect to this. And then we get possibilities like inside the net. So we have minimal model, or we have contraction. The curve. Maybe I should say in the beginning that I consider fully rational connected varieties for otherwise rationality problems become trivial. So our curve is side which is negative. On the fibers, this is extremal contraction. Or it's equal, and the degree of delta effect less equal than 4. You see, now let me explain.
Delta head is just the image, right?
Delta cut, yes. In each time, I told that yesterday that behavior of discriminant is this is just like B divisors. Each time it's just English. Let me explain the proof a little bit. Question? Yes.
Can you say something about the transformations above from xi to xi plus?
Yes, I'm going to explain this during the proof. It depends. First of all, we know that delta is a normal Gaussian divisor. And for any component, its intersection is not one. And this is because you see again our minimality condition. Again, you have this double cover, which doesn't split. And ramifications are in intersection points. Okay, and moreover, from this, we know that for any extremal curve, C, we have only the following. Suppose it's C square is less than 0, so it's birational. Then it is in fact -1 curve. And one of the following holds either C is not in the discriminant, doesn't meet discriminant. Either C is not in discriminant and C point is 1, or C in the discriminant and C intersect C by 2 points. Only 3 possibilities here for birational contractions. So this size.
Is the first one empty?
What?
The first case is empty.
Empty. Thanks. It is just let us consider just the first case, just to illustrate. It's a pre-image of C is certain there. And since it's not indiscriminate, it's smooth, so it's just some smooth surface. But it has a negative section. Minimal section. So if n is equal to 0, so f is E1 plus P1. I just discussed it as the first step. Next is by induction. Then you see we can blow down and in this case it has intersection -1 with both generators, so we just can complete diagram by regular. This is easy. If n is equal to 1, so it's F1. Then we can do this. Then I canonical class, and it's with sigma by 0, and right, it's an F. So we can make flow in this curve. So we start with each like this, we make a flow. This is simplest. I call it flow. So we get here, we just on the surface, we just blow down the curve and get one component outside. This is the picture after the flow, and then the proper transform of f is contractible. So the picture is like this: x flow prime, and then we blow it down in the complete diagram like this. Yes. In general, we have to make elementary transformations. We just blow up generalized transformations, blow up exceptional sections, and blow down proper transform of blow down proper transform of this area. After blowing up, the intersection number with rulings becomes -1, so it's contractible, and it turns out that this n prime strictly less than n, so this decrease n. We repeat this procedure several times until we get one of these cases. Yeah, I mean the firm. Pardon? N prime. What is n prime? N prime is we get here again over C. C is all f prime of C is again f prime, which is f n prime.
Yeah,
This invariant of Kirchhoff surface.
This is what happens also in n equals 1. You go up and you go down.
I think we should get this one. N is equal to 0. This is just easy computation. Other cases are similar, but a little bit more difficult to consider. Just really, the picture is like this, especially in last case. In last case, this surface is not normal because he's in the discriminant, so it has double. But anyway, we will go down this singular locus and get something similar like this. So it works. And we get issue like this. Now we are, and I recall that the dimension of this linear system are the same, so we can look at this minimal model. And what is important, we, in this case, we stay in the category of standard conic model.
Did you try this?
Pardon? High dimension. I think it's doable, but I didn't think about it. Yes, I think it should be. Possibly we have to allow singularities. Yeah. Okay. So what is consequence?
Where do you stop in this one? Sorry, quick question. So it's like induction on the Picard.
Yes, Picard decreases, and we stop each time we contract. If it's not NEF, then we have one extreme array. If it's birational, then everything is like this. If it's not birational, then it is either it's somehow modified space, it's either over curve or over point. Okay. What is the sequence? Pardon? Yes. Yes, of course, because this I told that I'm really interested in rationally connected correct. Okay. So consequence.
Ask again.
Yeah. So so the maps from Zi to Zi plus 1 are just, of course, contractions on a surface.
Yes.
The maps above from Xi
It's
to X
rational.
are but of course, but can you describe them in terms of MMP for something on the Xi?
I described it in one
Example.
It's just there are three cases. I exactly described first case. Other is similar. Completely similar. It's just explicit blow up and blow down curves.
Is it?
It's much more explicit than resolution of singularities.
Of course.
Just explicit curves.
I know, but are these transformations that are dictated by a minimal model program?
Not exactly. They dictated by you see intersection numbers. You see, I told you, for example, we say curve is -1. So we have here Fn. We have negative section. So we just blow it up, blow down the rest, and so on and so on. So it's explicitly described.
I agree.
Yes, I'm not. This is not exactly MMP because we first blow up, then blow down. MMP means that it's direct. We always blow down something. Here we first blow up and then blow down. So it's.
So are you asking that is it possible to have certain pair? Is it possible to have certain pair on the 3-4 such that you run an MMP for that pair turns out to be?
But anyway, you see, anyway on some step we blow up. Sir.
Yeah, I think I agree that.
Possibly we can, but I'm not sure. This is more closer. Sarkisian program. Okay, as a corollary, we have the following. Suppose 2k z plus delta is empty. Then either X is rational or X over Z is a birational square birational to which comes from a cubic surface. So our exception. Cubic three. Sorry. Okay. This how to can we see it? You see suppose so we have one of this we can assume that we have one of these three cases. In the first case K. KZ plus delta is net. But then by Riemann rule, we have H0. It is one, and this guy is positive. So why? Because the intersection of this guy is non-negative. So this case is not doesn't occur. In the second case, this guy is negative. So yes, this guy is negative. What does it mean? It means that intersection delta with the fiber is less equal than T. So we look at our X as a genic fiber over KT. What we get? We get Conic bundle. With at most 8 degenerate fibers. By our two-dimensional version, it is rational over even over this function.
So where's the section?
No section.
How about you need the
Yes, this is C1Q.
ah,
You see, I recall that we are on all algebraically closed field. This is C1Q. A good question, but still C1 field, and so Conic has a point. Okay. And moreover, you see, in the case this equal to 3, you don't need section because this is complex with degree 5 and so on. Okay, and finally, the last case. So already we have either if degree is less than 4, then we can reduce the previous case by blowing out point on the smooth point of the discriminant. Make weight change. Each F1, just blow a point on the discriminant, and we get make base change, maybe make standard model, and then we get here again for some projection to a curve with less than P degenerate fiber. But if degree delta is 5, then again we have two possibilities. It's either cubic base point to cubic field, or Barron's example. It's either rational or non-rational. This is the explanation. Okay. Now, the hope is that we can work with minimal models. Another evidence. This evidence was a conjecture. So one direction works. Another evidence is Prokhorov theorem. This was quite old. It belonged to many people and finally suppose the base is a ruled surface. Then the following equivalent. Three conditions equivalent. First, X is rational. Second, 2k x plus delta is empty. And third, the Griffith component of intermediate Jacobian is trivial. This is component of intermediate Jacobian, which is not a Jacobian of a curve. Some of it. So it means that intermediate Jacobian of X as a principal polarized variety is a sum of Jacobians of the curves. So this is another evidence of this. Let me explain how these ideas, how to prove it. Of course, from 2 to 1, you just proved it. I just know that the exception doesn't appear here because this curve cannot be embedded to Fn in a good way. From 1 to 3, this follows from Clement Griffith. And from 3 to 1, let me just explain. This for this I assume that for simplicity the delta is smooth. Of course, it's not like this, but in general, it is the same. Suppose that k z plus delta is empty. 2, 1, okay, 2. Suppose it's empty. In this case, easy computations with ruled surface shows that the intersection in the fiber is at least 4. And kz plus delta is basically free. Not empty. Not empty, yes. Converse is based on free. And it defines contraction. In fact, it defines smart field is some free n, This is either isomorphy or contraction of negative section. Okay. Then we look at the this map restricted to the this is canonical map. Okay, and now this all here is easy, but hard part is intermediate Jacobian says that suppose that J of X is Jacobian curves. Then the theorem proved by Malford. Then by Will. And in final version of Shakurov. Shakurov is for singular case. There is that delta is either ability, trigonal, or plane V. So hyperlytic is not possible since canonical map is birational. If it's trigonal, then the canonical map is contained in the surface of minimal degree, ruled surface, which should coincide with this thing. And the ruling here are gives us this trigonal linear series. So rulings are intersect the curve in 3 points. This contradicts this inequality. And plane clinic is also not possible for this curve. So this is just explanation. Once again, the hard part is this one, based on intermediate Jacobian. Okay. This once more evidence, but unfortunately, there is no reduction from this to this. We cannot say that this the surface minimal in this sense is minimal in classicals. So, okay. Anyway. Okay, what I have to say, one more, that there is subpicit theorem. The first statement here is generalizable. Also called theorem of Sarkisian. Says that in any dimension, in any characteristic, except the characteristic 2, says that if a standard conic bundle and this linear system is not empty, then it's Birational superregion. This is one more evidence for rationality criterion. The theorem is not hard. Maybe I'll explain it at the end, at least in three-dimensional case. The reason is that when we have then where our variety is far from being rational, then its birational structure is easier, and all proofs are also much easier. Okay, so now I want to apply Tarkisic program in dimension 3. In dimension 3, this is actually it works in any dimension, but I can formulate it in any dimensions, but I use it in dimension 3. Okay, so theorem says that if we have a rational map between two modifiable spaces, then it is composition of Tarkisic rings. Similar to that one, and this is a weak form. In fact, there is an algorithm how to do it. Very explicit.
For which field you are working? Which field?
Today, I think now I algebraically closed and characteristic 0
But if you want
for safety.
3 folds, can you do it for perfect fields?
Pardon?
If you want this for 3 folds, can you do any perfect field?
Characteristic 0. But since many things are still not clear. Moreover, I want to use more delicate three-dimensional stuff, so I prefer to use it in characteristic 0. We'll see. And Tarkisic rings are as follows. Maybe here. 3 types similar to that ones. Type 1, it's like this. We have modifiable space. Then we blow up something. Blow up in the modic category. Then we have log flips, and then we have modifiable space. Similar to this one, yes. Instead of just the only difference is that in dimension 2 we have no flips. Type 3 is inverse to this one, so we have x over that, then we have That we have blow down in more category. Type 2 it's just look like elementary transformation. And type 4 we have two wave fiber structure almost on the same so it's similar to this one. I define this right on the bottom denoted by T. I call this the base of the linear. So I want to apply this in our case.
So your type 2 and type 4 seems type 2 and type 4 seems quite the same.
What's the difference?
Maybe you want to go.
Yes.
You want to go up.
We have, sorry, we have blow up something like this. This one cannot be completed to the place. It's not trivial. So this looks like P1 cross P1 and two projection. And this looks like elementary transformation into fibers.
And there is no
T Y
law.
T here. It's a point. Then it's a point. Point. No. In fact, it can be, for example, this conic bundle is delta explication. Or something like this. For example, this both can be found. Which type? This conic bundle relative Picard number 1. Relative Picard number 1. There is no method in there. But no.
But this before in type 2 it was a simpler diagram, right? Before it was the same diagram. I mean, on why you can have it. I think the point is
There are two types. This type, elementary transformation.
but it's all the same base, right? In both
Yes,
diagrams.
yes.
But here you make a different basis.
And it is relative because of it.
Let me erase for a while.
And then it's on why.
Yeah. Sorry. You are right. You can like this. Yeah.
And the same Z.
Thanks. Pardon?
The same Z prime and second.
Z prime and Z. Yeah, but they was just related by this. Okay, thanks. It can be flipped here. Okay, thanks. Okay. Yeah, maybe you are right. You are right. You are right. Thank you. Thank you. Okay. So I run this program for our situation. So we have this now Conic bundle. Suppose it is not Birational region. So there is some map, non-trivial, and it is decomposed in a sequence of links. I forgot to say that in three-dimensional 3 we have worked with singular varieties, with terminal singularities. So even here we have a standard conic bundle. Then on the next step we have we may have singular ones. Even it is conic bundle, then it is still still have singularities, but in this case we have so-called conic bundle. This is Mori contraction. X to the surface equal. In this case, X can be singular. The base also can be singular. But the theorem is non-trivial of myself Mori is that in this case the base has singularities at worst dual. In fact, it can be smooth, but at worst it has singularities like this. So it's more or less controllable. And what kind of things we can hear here? If the base is the point. First, base is the surface. This is in cases 2 or 1 or 3. But in this case, the transformation is fiberwise. This link. Then the link is fiberwise. So we have here two conic bundles, but then of course we can take the standard models and as you told that the dimension is preserved. So it's controllable. What I'm going to say that suppose, for example, this is rational. I want to show that this linear system this linear system is empty. It's not empty. It's empty. Okay. So this control, if T is a point, suppose we have here conic bonds on the first step, we have a link over a point. What does it mean? I mean, it happens in this case. It cannot be because this is a surface. When I take here or here. In all these cases, Picard number of the base is equal to 1. Moreover, so what does it mean? It means that since we have this fact, from this we know that that I is the person is the Wilson gradient. And suppose we have a Sarkisian program, Sarkisian theorem. We know that by Sarkisian theorem, we know that for K plus delta, at least on the minimal resolution, is empty. It means that delta less equals than -4. So you see here we have del P with dual singularities. Such surfaces are classified. There are only few number of possibilities. One is P2, another P1, P1, 2, 3, which no. Only a few possibilities. The degree of discriminant is bounded. So for there are only a finite number of families for the discriminant. For each discriminant, we have only finite number of double curves. So in this case, birational type of conic bundle is bounded. Moreover, this bound is more or less effective. Everything is controllable and computable. It's there are a lot of cases to consider, but it's not like Newtonian induction. And finally, is a curve. It happens in the cases like this and like this. Then we can consider our link now over function physical by base. And so we that one of it induces Sarkis link on conic bundles over non-closed fields. So what can we have? We have one of the following. We have either X at the conic bundle, and then it is of this guy. Inverse. That's it. And here k x square equals to 3. And this is quartic delta. For type 4. We have surface with two conic bundle structures and okay. So here we have k x square equals to 1, 2, or 4. First two cases are in the first two cases, what we have, according to this explanation, we have Birational transformation, modular Birational transformation of x. This conic bundle pencil, there is Birational transformation which switches this conic bundle pencil. So this means that this modular Birational transformation is Faber-Weiss. So again, this dimension is preserved. So in these two cases, we just may continue, and we can control this linear system. The only thing we have to consider too, this 4, I told you that there is no involution, and this is 3. In this case, what we have. So we may assume that it is in the beginning. We have either transformation like this. This is conic bundle, two conic bundle, and then we have some flips, and I have y. This is quartic delta equation. On the left hand side, we have conic bundle with T, map over T. This is some ruling, and the discriminant is dominates T, and the map is generically degree 5. We call this conic bundle pentagonal. And another possible output, not output, but intermediate step, in which we stopped, it's like this. We have x prime. Here we have one conic bundle, another conic bundle, so that both sides are tetragonal. So delta point F is equal to 4. This is most closer to rational ones, according to this feature. And such a thing is called tetragonal transformation. What can we do next? We can proceed. Suppose we have at the end we have a rational variety. For example, P3. Then we have proceed here. According to this picture, we have here just quartic delta surfaces for a while, and then again we can only come back. So we can, after some steps, again get pentagonal conic bundle. So it's like this. And according to Skovsky's theorem, I formulated yesterday, the conic bundle over so in everything here is over the same base. So we can consider all the steps as a surface of a non-closed field. According to Skovsky's theorem, the conic bundle is unique, birationally unique. So again, we somehow came back to this. And moreover, on some intermediate step, here we have some slopes and relative Picard number 2. On some intermediate step, we get a variety with Shakurov called it central model. On some step, anti-canonical divisor becomes net. This is a speciality of two-rim game. Here on this side, anti-canonical class is negative. On this side, is also negative. And so, here after each flip, it changes, but on some steps it should be net. What does it mean? It means that on some intermediate step we have weak fun. According to BEB, weak fun is bounded. So links of this type are birationally conclusion. No, more or less this idea, but of course, want to prove that this links of this type, the whole stuff, is birationally bounded. But on this step, it is not effective. BEB is not BEB with varieties with terminal singularities. It's not. But anyway, we can for a while forget about it. The only thing we have to consider this tetragonal stuff. This is only abstraction to prove rationality. Let me give an example, geometric example of this transformation. Take P1 plus P1 plus P1 and divisor here of by degree, it is 3 degree, 2, 2, 2, smooth one. Anti-canonical, just anti-canonical divisor. And take a double cover ramified in this divisor. X. Then it has projections. For example, P1 plus P1. The fibers of the projection are double covers of P1 ramified into points, so this is conic bundle. And branch divide discriminant is easy to see that it is a curve of by degree of. We have another projection. In fact, we have three different ones. And this is exactly this exactly the trigonal transformation of this type. We have no such thing. No flips here. This is like this. In fact, we have three projections, and the explanation is that, in fact, this notion is close to Danagi tetragonal construction. In fact, what we have here the curve delta, which is covers our T of degree 4, and over this curve we have delta field in double cover. This is exactly Danagi data, and this satisfies the Danagi construction. Danagi construction gives some procedure to construct from this two more things like this. And in fact, these triples are classified. There are exactly 7 types, and our transformation preserves. And just to have to finish, what remains to do here? We want, for rationality criterion, we want to see that dimension of this linear system is preserved. But since it is trivial on the fibers, we need only to show that it is pullback of something from the base. So in our case, K is a pullback by start something on the base. And the same of the right hand side. What we need to show that the degree of this line bundles are the same. This is true in this case. And this can be checked basically locally by case consideration of these types. It's almost done. There is a local classification of these guys. For example, and in each case we have to we prove this. In fact, what's basic this most difficult part, most important tool here is canonical bundle formula. This canonical bundle formula today this line bundle can be decomposed in 2 parts: moduli and divisorial. Moduli is depends on the global variation, and it is depends on the corresponding elliptic curve, which is here. But divisorial part is local. It's locally computable. So it's is doable in many places. Okay, I stop here. Thank you.
So any questions?
Pardon? More part of this, you see, I almost explained last time. Once we have this transformation over the function field, we have mapped which is similar to just P1 plus P1. And this is double cover. In branch divisor is elliptic curve. Actually, we can. It has a model, some elliptic fibration over over T. And this gives us modular part of modular of the object.
Yes, so
This is like K3. Yes, you see.
the question is, do we know any compactification of modular of this variety?
The analytic construction is low. In analytically low.
We know the viability.
Pardon?
Viability of
Reliability? It's huge. You see, this is very far from being rigid, especially when we look at this. Even on enclosed field, even of the curve, it's huge. It's huge. Seems very interesting in varieties which are very close to rational. By any way, pliability, you should count it. Pliability here. For Conic bundles, how to count? There are a lot of maybe yes, but then anyway, in this case, it's huge.
And another question, so similarly to Sarkisov theorem, is there also a generalization of the second condition for birationally rigid?
What do you mean?
Like here on the left-hand side, for birationally rigid, is there a generalization to higher dimensions?
Of course, yes. Good question. I wanted to speak about that. I have no time. As a consequence of this stuff, what we get, I forgot to say, this theorem. This is theorem. Suppose that like this P take X plus delta is not empty. Then either X over Z is birationally rigid, or again X over delta over Z belongs to effectively bounded birationally. The proof included in this algorithm actually almost the same, because you see we used two cases just put here, and if it is not empty, then this step is excluded. So this doesn't work.
Any more questions?
Can I ask something? So can you say again in this other direction from x rational to 2x plus delta empty? So first of all, are there counterexamples to the statement? X rational implies.
You see that there is only one exceptional case. This is not a counterexample. Actually, people this is not conjecture formulated like this. If it's rational, then this linear system either is empty or there are exceptions. At the moment, we know just one. In dimension 3.
Yeah, the counterexample, you're adding.
So, for example, you just added yes, the conjecture is that strong conjecture. This is the only exception. Weak conjecture is there are only a few exceptions. At the moment, we almost shown that modular some finite number may be huge. But this is very popular now. Many people work with boundness and something like this, which is proved by Newtonian induction and something like this. This is not Newtonian induction. Even this step uses three-dimensional boundness. This is not very effective, but still there are constants.
Okay, so let's thank Yuri again. Yeah, thank you very much.